right, yes. So this is the physics part, even though Gerard said that he did physics also, so I will do a bit of math. What I want to do, so Gerard, he considered problems more related to classification, let's say between machine learning, math, and statistical physics, more related to classification or cases in which you want to recover a signal. So what instead I would like to study are problems in which you generate data, so what is called generative AI. So I will start with a very brief introduction to generative AI, and then we will focus on one topic in generative AI. So, well, just a brief history. So the history is short, but it's quite spectacular. So the generative AI, there are, roughly speaking, two branches. So there is the generation of text and the generation of images, sound, and videos. Now, for text generation, roughly, so let's say the way, so let's say the main idea, which is behind, for example, ChatGPT, that I think everyone has used at least once here, came in 2017 from a paper on what is called transformers. This is something I will not describe, but this is just to tell you and to show you what is the timeline in this kind of research. So in 2018, there is the research paper. 2017, there is the research paper. 2018, there is already the first application. And then 2022, there is ChatGPT. And there was the explosion of all this technique. Was implemented on a way which was open to all public all over the world. So it's an extremely fast acceleration between research and application. Now, what I'm going actually to focus on is, so transformers is one technique, and which is good for text, and that's not something that we are going to cover together. What we are going to study together is instead another technique, which is called diffusion models, which is very much related to out of equilibrium physics, and as I will try to show you, is very, at least for a statistical physicist like me that work a lot on out of equilibrium, it's really incredible. And so the first paper actually came from physics 2015 by Sol Dickenstein, Ganguly, and others that were thinking about out of equilibrium thermodynamics and what is called out of equilibrium thermodynamics, all the relation that came starting from Jarzynski, and they were thinking whether these kinds of idea could be interesting for machine learning. And they start really, I think the original idea came from them. Then I think it's, as I will explain, so the idea was nice, but then it wasn't clear exactly how you learn what is called the score. You will see what the score is. So there was a missing piece, and the missing piece actually came around 2020 independently from in computer science. And then I would say from 2020, then the field really exploded. In 2021, again, just 1 year later, there was already DAL-E, so it was already implemented commercially. And now there are many, many different implementations that use what is called diffusion models to generate. So first at the beginning was images. Now you can create sound, meaning songs, if you want. And now, I mean, in the last year, now they can create very, very good videos. Okay, so, well, generative AI, so again, what we're going to focus is really on generations of images, sound, and videos. And so the diffusion model, so this is an example. So for example, you have an image on the left. So it's the model has been trained on images of people. And so then what it can recreate, it's a new image of someone that does not exist, but looks really like if she existed. Then this is an example of images. Then there is an example of audios. You can try this Suno technique. I mean, you type Suno, and then you can create the song that you like with the text that you like. So just create a very faithful song in the style that you want with a text that is also created from scratch. And now you can do videos. Now the other thing which is quite interesting is conditional generation. So you can, maybe you can write a prompt. I want an image, for example, an angry bird, like the one which is here, and this is what is generated, which again is spectacular in a sense because first it looks like a bird, and second it looks angry indeed. So it means that the machine somehow it's able actually to do this kind of conditional generation. And then this diffusion model has also, I mean, a big potential for science, and I think I mean, they have not been already. I mean, they started to be applied, but I think we will see much more in the future. But just to give you some ideas, so for example, there was a nice paper last year on Lagrangian turbulence. So if you want to do simulation of turbulence, this can take a very long time. And the idea is, okay, if I can create fast new images, why I cannot create fast new configuration of a turbulent flow? And so what they did is they studied the case of Lagrangian turbulence, and they show actually that can create with this machine, I mean, short-circuiting completely all the simulation, create a trajectory that have all the nice multifractal properties that you find in turbulence. And so related to this, actually, the idea is also that maybe this technique can really be used to accelerated sampling. So sampling in science is something which is extremely important. I mean, sampling new configuration of a physical system, it's something that we use every time to study physical system. But sometimes sampling can take a very long time, especially, I don't know, if there is an energy landscape which is rough. And the idea is that maybe this technique works in a very different way and can provide a new way to have a very efficient sampling.
Yeah. Do you know if it's possible to impose symmetries on the...
Yes, you can do it, yes. So you in the, actually in, yeah, I mean, it will be more clear later, but yes, you can hard-code symmetry in in such a way that what you generate for sure will have the symmetry that you know that is there in physics. So in general, it's... All right, so this is just an overview of what these things can do, at least right now. And so what is the idea? So then we go, I mean, I will just give you the idea, and then, I mean, I will go to the blackboard and tell you how it works. So while we know in physics that, well, everything about equilibration, so when you have a system which is coupled to a heat bath, and if you write a simple equation on the dynamic of the system, the equation is the Langevin equation that I wrote on top with physics notation, in which you have so the dxi dt, xi would be the position of, let's say, particle I, is equal to minus the gradient of the energy plus a thermal noise. What we know is that, well, if you wait long enough under very, very general properties, this equation will bring the system to equilibrium. As we know, a system coupled to heat bath in generally goes to equilibrium. And so this is an example of a drop of ink in a glass. You wait long enough, and then the ink spread all over the place, and you are at equilibrium. Now, what this model do is that they use this idea, and they use it in using time reversal. So the idea is the following. So it's a little bit like the science fiction movie Tenet. I don't know if you saw it, but in this case, it's not fiction. So the idea is the following. They take this very simple equation, Øystein-Uhlenbeck equation, where xi, now you should think that, so the x is the vector which corresponds to an image. So xi is denote the value of the pixel I of the image. And so what they do is that they run an Øystein-Uhlenbeck process for each one of the pixel. And so when you run an Øystein-Uhlenbeck process independently for each one of the pixels, you go from a nice image, for example, of a dog, you transform it in white noise. Now imagine that you are able to time reverse this process, in the sense really from the point of view of the probability distribution. So you start from the probability distribution of dogs, you transform it in Gaussian, white noise. And now if you have you know how to do the time reversal, now I can pick a white noise configuration. I run the time reverse process, and this will give me, we are going to give me a new configuration of the original distribution, in this case of dogs. And so this is exactly what they do. So this, you pick up a white noise configuration. They know how to do the time reverse. And when the time reverse, they get a new configuration of the original probability distribution. So that's the idea. Now we are going to do I'm going to explain in detail how it works, but that's the idea. You have a process, very simple, Øystein-Uhlenbeck, that transform a complicated probability distribution in a simple one. You know the stochastic process which corresponds to time reversal. So you pick one configuration of the simple probability distribution, the white noise. You run the time reverse process, and this will give you a new configuration that you didn't see from the original probability distribution. OK, so I think this is all I wanted to, just a very, very brief introduction. So the outline of my lecture is, the first one is, so today we are going to do theory of diffusion models, and we'll see that it's very much related to out of equilibrium physics. Tomorrow I will tell you about formation of features. So I mean, when you have images, or in general data, there are some important features. I don't know, if I give you images, you can have, in the images, you can have, I don't know, different kinds of animals, for example. And then within the animals, you have the different species of animals. And then within the same species, I don't know, you have different colors for the animals. So all these are high-level features. And I wanted to understand in the process, in this generation process, how these things are generated. And we will see that this is nicely related to dynamical phase transition, so phase transition out of equilibrium. And then in the third lecture, I will tell you about generalization versus memorization, because sometimes actually this method generate images, but they don't generate new images. They just generate the images that you have used to train them. And that's bad. So this is called memorization. They are not, I mean, they just learn by heart the image that you gave to them to learn. And you don't want this. You want to be in another phase, which is called generalization, so in which you create images that the system has never seen. And we will see that actually this transition, well, is not fully understood, but I will tell you one part that we have understood, and the part that we have understood is nicely related actually to a problem in disorder system and to the random energy model that actually Gerard already discussed a bit. So the nice thing also, I think, of this topic is that, well, it's really at the crossroad of many different fields. So the methods are methods that come from statistical physics, if you want to study diffusion models. But then there are methods actually which come from high-dimensional probability and probability in general. And then, of course, methods that come from computer science. And also, I mean, today we are going, and I mean, during this lecture, we are going to see to this problem from the lens of computer science. So we want to understand why these models are generating faithful data, good data. But this actually is related to other problems in probability, for example, transport of measure, because what we are doing is we are creating transport from a difficult measure to a simple measure and back. It's related to something which is called stochastic localization, which I will not describe, but if you want to know more, Thierry work on this. It's related to sampling. Many people start to study this to perform new ways of doing sampling. And there is a very, very, very nice relationship with the renormalization group, which is not really completely related to to the main topic of my lecture, but since it's so nice, I'm going to spend at least 10 or 15 minutes to tell you about this. All right, so now we will switch to the Blackboard. Yeah, there's a question? No? Okay, if there are no questions. All right. Okay, so maybe let me just start with what the problem is in a, let's say, in a math way. So the idea is the following. So we have data. So the data will denote it A mu. So data are in RD. So it's a vector in D dimension. And so the number of data mu goes from 1 to small n. A mu is, so we think that is taken from a certain probability law, P0 of x. But the thing is that you don't know P0 of x. The only thing that you get is data. So the only thing, this is what you know. And from this, actually, you want to sample new data from P0 of x. So somehow, you could think you should have to be able to learn P0 of x in some way. So you have the data, you want to sample new data, and this new data should be, in principle, data which is sampled from P0 of x. Okay, so this is the model very, very roughly. Maybe you can also consider cases in which instead of P0 of x, you have P0 of x condition on something. So this is the example that I gave to you. For example, I say, I want an angry bird. So this would be the angry bird, is the conditioning. And then I want to sample from a probability distribution with some conditioning. Okay. Yeah?
But your data wouldn't be angry dogs or angry birds, right? You would have some angry persons and some birds, and you would like to mix them, but you wouldn't have angry birds data, right?
Sorry, I didn't understand
the data you have doesn't follow P0 of X conditioned with C, right?
Yeah, so maybe can we wait to discussing the conditional just next lecture? I will tell you exactly how people do for the conditional. For the moment, it was just to give you an idea of what you can do. And so now this thing, why is difficult? So let's do it. If you want to do it in one dimension, okay, one dimension, there is no problem. So let's say let's do it in one dimension. So in one dimension, I have, let's say I have some data, a mu. If I have data a mu, what I can do, I can construct an histogram of the data. So let's say I do the histogram. I don't know if I have data, this histogram will be roughly like this. Let's say, that's the histogram that you can create from the a mu. If you have the histogram, let's say that then you I don't know, you do something which is an nice interpolation from this. So in one dimension, you have this line. This is your estimation of the probability distribution. From this, you sample from it. Very easy, no problem. So that's not a difficult problem in one dimension. Now the thing is that for real data, so the data that you have seen, for example, let's think at an image, I don't know, 300 by 300 pixel. Well, actually, if it's, let's say, in black and white, so 300 by 300, it's already, the dimension d, it's of order 10 to the 4. So it's now it's not one dimension, so this was d equal 1. Now you are in d equal 10 to the 4. And now 10 to the 4, it's the space. When the space is very large, then the problem becomes extremely difficult. So why is that? So there are what is called the curse of dimensionality that I'm sure that you have heard about. The curse of dimensionality tells you that in the worst case scenario, the number of data that you need in dimension d, it's of order of exponentials times a constant times d. So it's the number of data that you need to have, to be able to do this construction. And not only this is the number of data, if you can also ask, okay, how many parameters will I need to construct this function? So how many parameters I have to fix, for example, in the neural network? Well, the number of parameters, let's call it m, is also going to go like exponential with another constant times d. So in principle, at least in the worst case scenario, in high dimension, this problem of generating new data, if you have this data a of mu, is very difficult. And so from the data, from the dimension that you have in practice, well, you could say, okay, that's impossible. But in reality, you have seen it's possible, people do it. So of course, there is a big question is why you are able to do it. But in any case, what I wanted to tell you, just to start, is that the problem is challenging in principle. And a big challenge is understanding actually how, in practice, with this method, you can do it. OK, so now how you do it for images, video, and sounds. So what you do is that you time reverse a Langevin process. So first, I would like just to recap a few things about the Langevin equation that I'm going to use. So the Langevin equation, so I will use the notation of physicists. So the xi dt minus dv dxi plus eta I, and eta I of t, eta j of t prime is equal to twice the temperature. So Kb, the Boltzmann constant, is equal to 1. So this is the Langevin equation. And I know that this is a school between mathematician and physicist. So I know that, this is the physics notation. So, as a mathematician, you would write maybe, you tell me, something like this, plus maybe square root of 2t dbi of t, where this is a Brownian. And instead of using this, you would use expectation. OK? OK. I hope you are fine. We are between friends. I would use the physics notation, but I can go back to the math notation if it's unclear. OK, so if you have this Langevin equation, so what do you know? Well, first you know that the probability density of pxi t under very general hypothesis, when t goes to infinity, goes to equilibrium. So it goes to the Boltzmann-Gibbs or Gibbs-Boltzmann distribution, which is equal to exponential of minus v of x xi divided by t divided by the partition function. Okay, and so maybe let me do just an example just on this side, which is the Oystein-Uhlenbeck process, that it's useful because it's the one that is going to be used in diffusion models. So in this case, v of xi is equal to xi squared divided by 2. so is the potential which is just like this. So it means that, well, this, what I wrote there, it means that, I mean, I can start from wherever I want. The particle, let's say, that start from here at t equals 0, but then, while it moves, subject to thermal noise in this well, and then at the end, it equilibrates, which means that the probability pxi of t goes, when t goes to infinity, to exponential of minus vxi of t, which is minus xi squared divided by 2. And let's take the temperature equal to 1, as they do in the diffusion model. So t is equal to 1 divided by square root of 2 pi. OK, just a Gaussian. So it's n01. OK, so this is another thing that we are going to use. And then the final thing that I'm going to use is that there is a probability, a PD associated to the evolution of this probability law. And this PD is the Fokker-Planck equation, which is dt of p of xit equal to, OK, let me do it in a high dimension. So if x, so maybe I should write this way, meaning that, or maybe with a vector, let's say. OK. OK, so now you have p of x. And this is sum over I from 1 to d of dxi of dv dxi plus t dxi applied to p of xi of x and t. OK, and this is the Fokker-Planck equation. OK, so this is all the things I need for the analysis. Yes.
After averaging over all initial conditions.
So this, well, this is, so you start at t equals 0. You can either, you can choose what is the initial probability. So let's say p at t equals 0 can be either, a fixed initial condition. So let's say dx minus x in a given point. Or you can start from a certain p0 of x. So in any case, you go there. Question? No? All right.
You always have the different pixels go independently?
Yeah, yes. So that's, yes. So in diffusion model, yes. Then you can ask, why just use this equation? Can we think to something else? Can be, and this, I'm coming to this, and actually the relationship with the normalization group, it's the first step in this direction. OK, so now, if there are no questions, let's start to discuss the diffusion model. OK, so in diffusion model, or, yeah, I hope you see it. So there are two processes. There is a forward process, in which you start at time t equals 0, and you run the Oystan-Uhlenbeck process. So here you have the Oystan-Uhlenbeck process, which is the one that I wrote there. You run it independently for each pixel. And so you have, well, your image that is transformed in white noise. So here you have the data. So let's say that you have the original probability distribution, b0 of x, if you think that you work in probability. And at the end, what you get here at the end, at very large time, you get the Gaussian. So n0 identity. OK? And now also the things that you know is that, the Oystan-Uhlenbeck process actually converges to equilibrium very fast, exponentially fast. The relaxation time, it's of order 1. So actually, when I say you go to long time, it's not that long. When the time is 10, you are in equilibrium in general. And now, well, there is the question is, OK, how we go backward? So then we have a backward process. So let's say that you go from time t equals 0 to a certain time tf. And now we want a process that comes back. So here is a tf. You start at tf, and you go backward. So let's say that I define a time which is tf minus t. So tau here will be 0, and will be equal to tf here. Now the question is, what is this backward process? OK, so now let me give you another result, which is, I think it's standard, even though maybe it's not so widely known. So so let's say that you have a Langevin equation, dx dt. So now I will not put the index just to be a little bit more simple. So minus dv dx plus psi of t. And so this will be our process forward. And so psi is the usual Langevin noise. So psi t prime, which is equal to 2t delta of t minus t prime. And now you go from P0, which is the original distribution, to some distribution which is PTF of x during this forward process. Now, what is the backward process? Now, the nice thing of the backward process is that you can construct actually a backward process which is just a Langevin equation. So you come back using a Langevin equation. And the Langevin equation that you are going to write is this one, dx d tau, which is equal to minus an effective potential which depends on time. I don't write the time, but it depends on time. Plus another noise, so let's say, but which has the same statistic of this one, psi of tau. So psi tau prime is equal to 2t delta tau minus tau prime. And now what is this VF? So VF is equal to, or maybe let me write it this way, dVF dx is equal to minus dV dx, so exactly minus the force that you have here, plus another term, which is minus 2, the temperature, and here you have the derivative of dxi of, well, no, without the I, of p at time t, or p of x, of log of p of x at time t. So now what is it? What is this? So p of x at time t is just the probability distribution at which you arrived here. So at a given time, you have you go from p0 of x, you arrive here, you have px of t. And now what this is telling you is that, well, the force that I have to you to, when I'm here to go back, well, I can construct it is minus the force that I have in the Langevin equation, minus 2 times the temperature, and then you have the gradient of the log of that probability distribution. Okay? And this thing is what is called the score function. Okay? That's a result that now I'm going to prove. And if you do this, so you can go back in time, and you can even actually prove that even at the level of the trajectory, you're really doing the time reversal. So the probability of the trajectory of this process are exactly equal. So I mean, if you take a trajectory, the probability when you do along the forward process is equal to the probability along the backward process. Which means that, in a sense, if I have the movie, which is running this way, if I just run the movie backwards, it's just, you're going just to see the trajectory of this process. Okay, it's really, really time reversal. Okay, so now, of course, the question is, okay, how I'm going to learn, how I'm going to learn this. This will come. Yeah.
Hello. I was wondering, when you say you go backward, does it mean you recover the probability for isolated pixels? Because you don't get the correlations between neighboring pixels, do you?
No, you get it because actually, so when you go forward, you have a Neustadt-Uhlenbeck process in which you go forward independently. But when you go backward, the force contains interaction between the pixels.
It's on the whole vector.
It's on the whole vector. Yeah. I should put the, so let me put the vector here. Yeah. So in this way, it's independent. But when you go back, this potential, it's really giving the interaction between. Otherwise, you're right, it would be impossible to get the correct probability distribution. Yeah.
The coupling is just in P, right?
Yes, the coupling is just here. Yeah. Other questions? Okay, so let me now show what is the just to prove that this is the time reversal. Well, what should I do? Sorry. Okay, so how we do it? So we are going to do it using the Fokker-Planck equation. So So what I have is that since I have this backward process, so in this backward process will satisfy the Fokker-Planck equation for this backward process. So the P, let me take the notation that I have here. I'll call it P backward, tau of x and tau, satisfy a Fokker-Planck equation. So what is the Fokker-Planck equation which is satisfied? It is going to be d tau backward, which is equal to, okay, I will not put the, so let's say dx. Let me do it in one dimension because it's the same. I mean, so it's more simple. Okay, t of dx, and then I have minus dv dx, and then I have minus twice the temperature, and then I have the derivative with respect to x of log of p and x and t. Now, this t in reality is a function of tau, remember. So at time tau, what I have to, when I'm here at time tau, what I have to do is I have to read what is pvx of t. I take the log, I take the gradient, and I use it for the force. In the following, I will not put necessarily that's a function of tau, but it's a function of tau. Okay, and here I have p backward of x and tau. So this is the equation satisfied by this. And we have, as initial condition, we have p backward x at time t equals 0 is going to be equal to p of x at the final time.
So this t of tau is just tf minus tau or something?
Yes, it's just that, yeah, it's t is just tf minus tau, exactly. Yeah,
Nothing complicated. No, not a complicated problem.
No, then indeed, then you can ask a twist, you can say, okay, maybe you can change the clock, and this can be done, but I'm just being simple. Okay, so now what I want to show that this, we are going back doing time reversal, I want to show that the solution of this equation is going to be, so pb of x and tau, what's going to be, the solution is just equal to p, let's call it, it's p of x and of t of tau. Okay, so it means that the probability that I get here along the backward process, or x at time tau, what is it? Well, it's exactly this probability that I have along the forward process. Okay, so when I run in this way, I'm just actually, just getting exactly the correct probability distribution. Is it clear?
So if I was to be a naive physicist still, so you're going from something cold to hot, and then you're going from something hot to cold about the process. Yeah. But there's some cost if I'm still a naive physicist, right? And then the cost is in this.
Well, I mean, the cost is, okay, how I can say, I mean, it's the cost in general. So, well, you have to learn, I mean, the difficulty is that you have to learn this log px of t in practice. Like now, in terms of cost,
which is like a potential, right?
I know, which is not a potential, yeah, no. It's true that, I mean, you, in a sense, I mean, you're really changing, I mean, in one case you have the entropy going one way, in the other you go backwards. So you're really doing something to the system which is completely unusual, because you're using forces which are really tailored to make you to going back in time. Yeah.
Yeah. So this effective potential, I mean, if you average it, it kind of looks like a free energy, right? Because like expectation of log p is entropy. And then
yeah, indeed. I mean, if you look at this, log of p, it's a little bit what was called the instantaneous entropy in stochastic thermodynamics. So indeed, this is like the gradient of the instantaneous entropy. So it's maybe that's a way to interpret why this can allow you to go back in time. Is answer to your question?
Yeah, the physical interpretation.
Yeah. Okay. So, well, how we show this? So remember, so px and t, we know that it verify the Fokker-Planck equation forward. So it means that px and t verify the equation, which is dp dt, which is equal to dx of t dx plus dv dx p. Okay. So what I'm going to do now is that I'm going to I plug these ansatz inside here, and I will see that it verifies this equation using actually the forward equation. So let's plug it. So when I plug inside here and I change tau in t, what I get on the left-hand side is I get d minus dp dt. Okay, I just take this, I put it here, d tau becomes minus dt. So this is what I get. And on this side, what I have is dx of t dx. And then I have minus dv dx minus 2t. And now let's take the derivative here. This is going to give me 1 over px and t of dpx and t dx. And then I have p of x and t. OK? All right, so now, well, look at this term and at this term. Now, we here have 1 over p and I have p. So the 2 goes away. And I get minus 2t, the derivative of dp dx. And what is this term? Is t, which acts on p. So is t dp dx. So actually, these two terms are the same, except that this has a plus 1 and this has a minus 2. OK, so what I get from here is I get a minus. So the derivative with respect to x. So I put a minus outside. And I have dv dx. So this is this term. And then I put these two together. And this gives me minus, sorry, still a plus. So it's minus 2 plus 1. It's a minus 1. And the minus goes outside. So it gives me t of dx, px and t. OK? Are the manipulation clear? Otherwise, you tell me. OK, so if are clear, well, now what I have a minus on this side. I have a minus on the other side. So I can take the minus. So I get that the equation is indeed the one which is verified by p. So OK, so this is indeed the solution of this equation. And it has the correct boundary condition because, well, by definition, px at tf is px at tf, and px at initial time is p0 of x. So indeed, actually, this is the part on the right is the time reverse of this process. Actually, there is a little bit, if you want really to show that at the level of the trajectory you have time reversal, you should do something more. And I leave you this as an exercise. Think about what you would do if you want to show that the probability of the backward trajectories is equal to the probability of the forward trajectory. And this is actually, it's very similar. The computation that you have to do is very similar of what you do when you do this Jarzynski relationship, you will see. So think about it. You have, I know you have some free time, so. OK, all right. So now, well, that we have established this, so now we know what we have to do if we want to go backward in time. So we have to use this force, this generalized force, to go backward in time. And so in principle, if we know this force, well, we just take a white noise. Let's say this force for generating images of people, for example. We take a white noise configuration. We really run the Langevin equation. The Langevin equation on the pixel will give us a new image of people that do not exist. And to me, again, as a physicist, thinking that this is indeed what they do. So I mean, they really run Langevin equation. Or sometimes they run also something else as a flow equation. I will tell you later. But in many cases, they run a Langevin equation to create all these amazing images, video, and sound. And sounds. It's really mind-blowing. Yeah?
If your initial distribution at t equals 0 has an atom, which is the case when you have sampling, I mean, when you have a sample, then of course this force becomes very singular.
Yes.
And so simulate using this becomes impossible at the end of your simulation, right?
Yes. So in practice, yes.
Log of, I mean, if pt goes to a Dirac mass or whatever, this grand log pt will become very, very unstable at the very end, right? At
the very end, yes. So in practice, well, first they discretize, and they then never go extremely close to the final point. But then also, if the system is working, so you're right. So this will come in my third lecture. So when you have memorization, what happens is that you start from points. I mean, Dirac, so the P0 is just a sum of Dirac points, which is the initial distribution of the data. And what you don't want is the system generate exactly this distribution. So a sum of Dirac peak. So you want to be in a generalization phase when the system, even if you give a P0 initially, which is a sum of delta peaks, it gives you the true, I mean, a good approximation of the true underlying P0 of x. So in general, you work in a case in which you don't have this. But sometimes when it does not work, when you are in the memorization phase, you get something which is quite singular, but since you discretize, it's not.
So this transition, memorization, generalization might be seen as a consequence of this singularity at the end?
Partially, yes. Yeah. Okay, so are there questions? Yeah.
Do you need to be at equilibrium for your Langevin equation or for your reasoning?
No, not at all. So this is really completely out of equilibrium. So you start from, the idea is really you start from a probability distribution P0x out of equilibrium, and you arrive to a probability Pt f of x. And this is completely general. So this just time reverse the process. So it's true that the time reversal in physics, in general, you think about it when you have equilibrium dynamics, and you see, well, I'm in a steady state, and I'm in equilibrium, and then I have time reversal of the trajectory. So this is a more general time reversal. So you are out of equilibrium, and you have a process which is the time reverse of the one which is the forward.
And so, for instance, you don't need necessarily to have a gradient dynamics.
No, you can put a force, indeed. It's just that for the Einstein-Uhlenbeck, it's a gradient, but you just put a force. Yeah. Okay, so now I would say the questions that block many people for some time is, how do you learn this score? So the problem is, so the idea now, the problem is, in a certain sense, is well posed. So I do Einstein-Uhlenbeck from the data, and so I have many trajectories. But from these trajectories, which are the evolution of the image under the Einstein-Uhlenbeck, I have to learn the score. And the score is the gradient of log p. And p, as Gerard was saying, is a sum of delta peaks. Doesn't look like a good thing now, how we are going to estimate this. So now there is a twist. So there is a very simple, actually, way to transform, to learn, actually, this grad of log p, which is called the score, and what I'm going to tell you right now. But this is really, for example, what in 2020 really switched, and people understood how you can learn the score in an effective way. Okay, so now what I want to do, what I want to tell you is how do you learn the score? Okay, so, well, so how do you learn? So the difficult thing that you have to learn is what is called the score. And so what you're going to do first is you have to use a model for this function. So what is this? So the score, let me write it this way. Maybe what notation should I use? So I will use this notation, S of x and t. So it's a function in RD, from RD to RD. And as I say, D can be very large. So this is, in principle, it's a complicated function to learn. And so what you do, I mean, what people do, and is that they use a neural network representation for this function. So they construct a function which is S theta of x and t. Theta are all the parameters of the neural network. I will not tell you, actually, I will not go over, I mean, I will not tell you what kind of neural network they use. I mean, it's typical structure of neural network in the sense that, as I think Gerard already told you, so what you do is that you do matrix multiplication, nonlinear activation, matrix multiplication, nonlinear activation, and so on and so forth, with different layers. So there is something that is used in particular, which is called UNet, but I will not tell you what it is. And if you want to know, I can discuss at the end, maybe, because it's not something that I'm going to describe. It's not described in my lecture. So for the moment, what we just have, what you just should think is that this is a multidimensional function that you can adjust, fixing the parameter. The number of parameters also in typical application is huge. I don't know, 10 million parameter, for example, that you have to use. And so how you fix this parameter? So what you're going to you're going to use a loss function. So you construct a cost function that you want to minimize in order to get this. And the loss function is defined, let's say the loss function at time t is defined in this way, like, let me do it this way. So it's the integral over dx of px and t of s theta of x and t minus the grad, so the derivative with respect to x. So now this is a vector. It's of log of p of x and t. So this is the theory. We are at the level of the theory for the moment. So this is the kind of loss function that you want to minimize. So let's discuss a little bit why this one. Well, first because it's like...
sorry, you should put that back. Don't worry. Okay, vector will work.
Okay, so this is just, it's like a regression problem. So you have a function that you want to learn, and then you just minimize the square of the difference. And now the important thing is that, well, since, well, how you do it integrating over x, px, and t, and this, I think, well, this is normal because in principle, since this is a multidimensional function, you want to learn it on typical value of x, meaning that the x follows some trajectories, and you don't want to learn, you don't need to learn, I mean, this function on very rare trajectories. You just want to learn it on the part of the space which is typically sampled along the forward and the backward process. So this is why you put this px and t.
But you cannot do this integral in practice, right?
No, you cannot do this in, well, let's see. No. Well, okay, let me go at the end and then you will see. Okay, so for the moment, in case this you cannot do it because you have the grad of log of p, so you don't know what to do with this. Okay, so now let's work on it a little bit and to transform it in something in which you can work. Okay, so let's rewrite this like, sorry. So there is maybe remark number one was that, I mean, why this loss is good is because, well, it's just a regression problem on typical, it's a regression problem. So this is a loss which is natural. And the other thing is that actually there is a bound that I will not describe, but it's a bound on the Kullback-Leibler distance between the probability P0 of x and the probability that you get with the diffusion model of x. So it means the diffusion models means if I use this S of theta, and then I start from PTF of x, and I go back, here I generate a probability distribution. It's going to be PDN of x. And now the Kullback-Leibler divergence between these two can be upper bounded by the integral over dt from 0 to tf of, well, this L of t. Okay, so this tells you, that's good. It tells you also that if you're very good in minimizing this, actually, this is going to be good. So,
okay, that's another good thing.
So this is always true. This is not only for UNet, for whatever you do.
Yeah, whatever. Yeah, exactly.
So this is just telling you that this loss, it's a good idea. All right, so let's work a little bit on this loss. Okay, so something that I didn't tell you, which I will do it now, just that it's useful, is that which is another way to see. So if you integrate this equation, I just need an extra result that I forgot. So if you integrate this Einstein-Uhlenbeck equation, you get that x at time t is going to be equal to x0 times exponential minus t plus the integral between 0 and t of exponential of minus t prime of eta of t prime dt prime. So this is the the solution of this equation with the initial condition x0. Now, if you stare at this, what this means is that x of t in probability, also in distribution, is equal to x0 exponential minus t. So you take initial probability distribution for x0, you take exponential minus t. Now this thing here, it's an integral of Gaussian variables. It's like a sum of Gaussian variables, so it's a Gaussian. And if you just compute what is, so the mean is 0, you can compute the variance, and you will see that this is, in distribution, is just equal to 1 minus exponential minus 2t, and then a Gaussian variable, gt, which is just n 0, 1. Okay? So you see, this is also here, you see why in computer science this It's like noising the image, because what you're doing is that you take the initial image, you reduce the amplitude of each pixel, and you add the Gaussian variable. And at the end, when t go to infinity, you see that when t go to infinity, this term goes to 0, and this term just go to g of t. So just go to the Gaussian. Okay. So you transform the image in the Gaussian. Okay, this is just something that I need, but you see why this is called noising. And so in computer science, I mean, the backward process that we call Langevin time reversal, they call it denoising, because it's like you denoise an image. The incredible thing is that you denoise white noise to get an image. Okay, so now let's work on this.
Sorry, one question.
Yes.
About this. Yeah. So DCT, is it correlated in time?
Yeah, it's correlated in time. Yeah.
Okay, so it's just not linear.
It's not linear. Okay. Okay, so if we work on the loss, so let the loss L of t. So what we get, well, we expand. So we get dx px of t. Then we have s theta of x and t squared. Then you get minus twice the integral over dx px t, s theta of x and t, dx of log of p of x and t. And then we get the square of dx log px of t, but this is something which does not depend on theta, so it's just a constant, so we don't care, because remember, what we want to do is we want to minimize the loss with respect to the theta, which are the parameter. So this is a constant with respect to the parameter, so we just write constant, it's not important. Okay, and so now, well, let's look at this term. So this term here, what is it? So I can rewrite. So here, I'm going to get exactly the same thing. And here I have minus twice the integral over dx, px and t, s of theta, x and t. And here I have 1 over px and theta of d px t dx. Okay, and the px and t, which is here, goes away with the px and t, which I have here. Okay. All right, so now we need an extra step. What is the extra step is, well, we have to know, well, this, we can do this derivative if you write explicitly what is pxt. Now, what is pxt? We do it here. So pxt is equal to the integral over dx0 of px0, and then the probability of x, let's call it xt, given x0. Now, what is this probability? Well, we can read it from here. What is px, the probability of x of t given x0? So x0 is given. What is the probability of px of t? Which kind of law it is? No, Gamble or? Okay, I don't go on if you don't tell me. Come on, so what is it? Eh? Okay, I will do it for you. So I'd say if I fix x0, well, this is a Gaussian, so the probability of xt, it's a Gaussian, right? Okay. All right, so what is it? So what is this probability? Well, you can read it from there. It's just exponential of minus. So it's x0, exponential minus t. So I just do one, minus x square divided by 2, 1 minus exponential minus 2t, and then square root of 2 pi 1 minus exponential minus 2t to the power of d. Okay, and so now this is nice because now you see that if I rewrite this is dx0, dx0, and now the dependence in x is here, so I can do this derivative. So let's do the derivative with respect to x. So what I get here is I get same term minus twice the integral over dx, and then I have s theta of x and t. And then when I take the derivative with respect to x, what I get is that there is a minus x minus x0 exponential minus t divided 1 minus exponential minus 2t, which comes down. And then, well, and then I have exactly the same thing, so I'm going to get p of x0 and p of x of t given x0 plus a constant. Okay? Okay, now
What happened to the integral over x stars?
yeah, I forgot it. You're right. Thank you. Okay, now it's correct. So now I can repack all this in a way which is nicer, which is now I rewrite this and I first write it and then I come and I will discuss this. I rewrite it as a square, like s theta of x and t, and then I have plus x minus x0 exponential minus t divided 1 exponential minus 2t. I'm sorry, here there is. So it's dx0, dx, p of x0, p of x of t given x0. And then I have a square, and then I have another constant prime. OK, let's see that it works. Why it works? Well, if I take the square of this, well, the first term is going to be, well, the integral over px of t of s theta squared, which is this. And when I take the product between these two terms, well, minus and minus give me a plus, and I have this times px0, px of t given x0, which is what I have here. And then I have the square of this, but again, the square of this does not depend on theta, so it's just a constant, and so I'd include it inside here. OK, tell me if it's OK. Questions on the loss? Now, why this loss is nice? Because this, for the moment, we are at what is called the population loss. So for the moment, I wrote it with the initial probability distribution, and then everything is with the probability distribution. But now this, so I can, let me write it in this way. So the loss at time t, let me write the mathematical term, is over x0 and x at time t. And then I have s of theta of x t, t plus x t minus x0 exponential minus t, 1 minus exponential minus 2t squared. OK, now I forget the constant. I just don't put it because we don't care. OK, so this is what we have to minimize with respect to theta. But now this, we can easily write it in terms, actually, of data. So what I have to do, I have just to imagine what is the data that I have. So the data, you have to think that I have, let me do it like if we were in one dimension, we have trajectory. So this would be the a mu. So this is time. And this would be tf. And this is 0. So we have just trajectories. And what I have to do, so I have a certain number of trajectory. In principle, you can have multiple trajectory for a given data. So I can rewrite this in the LT empirical is just 1 over the sum over, let's say, of all trajectories. And then I sum over all trajectories. So this is the sum over the number of trajectories. And then for each trajectory, so for each trajectory that I have, let's say this one, what I have to say is, OK, I have an initial point, which is what I call x0. And then I put it inside. So I have s theta xt t for this trajectory, plus xt for this trajectory, minus x0, the initial condition of this trajectory, exponential minus t, 1 minus exponential minus 2t squared. And I sum over all trajectories. I just need to know the initial point and where the trajectory is at time t. I do the sum. Actually, and in principle, and then I can minimize with respect to theta to get the parameter that I need to learn the score at time t. Actually, what they do is not this. They define a L, which is the integral over, or the sum, more, the integral over dt of some parameter, some weight, lambda of t, of L of t. And L of t is a function of theta of t. And then they just minimize this. So in one shot, you get all t theta. So it means that you get the entire score function at all time. Sorry, the notation is not this one. Is s of theta of x at all time, t of theta. Okay?
But here in this integral, it's also an empirical version.
Yeah, it's empirical. Yeah, empirical. Thank you. Yeah.
It's just like extremizing an action, right?
Yeah. You can, yeah. Yeah.
Is there any reason to pick lambda of t different from 1? Because the thing that you said bounds the KL divergence is just the integral of LT.
So, well, yeah, if you think it in math way, you would say maybe you should take lambda t equal to 1. But then it's true, for example, what says Gerard is that the depending, well, if you write it in this way, you see that at small time, things blow up. And then in practice, they just don't care. They choose the best lambda t that give the best images in practice. It's not that there is a theory behind this. Let's say it's called an hyperparameter, and then they work and try to fix what is the best one.
And you can still use this to bound the KL divergence?
No, you cannot.
Okay.
Other questions?
So this could be done for any s theta, not only for unit. So.
Yeah, this is completely general. Then what you choose for s of theta can be a unit. For simple case, for simple images, for example, for minced, you can just use a multi-layer perceptron. It works. For difficult images, the architecture that you put in s of theta, it's more complicated. So you have to use the unit.
Yeah, because as we've seen, the choice of the loss function might change the algorithm performance.
Yeah.
So if I understand well, it means you have to choose an s theta such that the minimum of the population loss is really what you want, and then such that this algorithm works decently well.
Say it again. So you have to choose an s of theta
such that the minimum of the population loss is good.
Can approximate this score, yeah, and then
and also such that the algorithm is not too painful.
Yes, exactly.
And unit is good for a certain class of.
Yes, yeah. Other person, yeah.
So it seemed at first that you want to learn theta, the score of x and t with the theta regardless of t. Why do you not learn like a score for each time? You use a unit for each time or something like this?
Sorry, no, I agree.
So the s theta of x and t, it seems that it's one unit for the overall process.
No, sorry, I was wrong. So there I started first with this theta is theta for that time t. So at each time you learn, let's say.
In the end, that's what you wrote.
Exactly. I'm sorry. No, so there I was just first in thinking at fixed time. So you learn a unit. In practice, they learn a big unit in which the time is a parameter, and they optimizing this loss. Yeah.
Giulio. So if I try to rephrase the problem, there is a p-naught that exists, which is the distribution of all possible images that exist in the universe. Then your data is an empirical measure which has n samples, and then you will run this forward and backward route to try and guess the true p-naught of all the images in the universe.
Yeah. To actually sample from this way. You don't want to know the probability, you just want to sample.
Do we know conditions under which this should work? Because I can understand if you do it very well, you learn back the data, so you memorize. But do we have a clue of why we can, what are the conditions on the distribution and the number of samples such that this process can actually represent the global distribution?
So there are two. Okay, let's see. So I think it's okay. What are so first? I mean, as usually in machine learning, there is something that should be easy on P0 of x, which means that it's true. I mean, it's the volume in high dimension is very, very large. You get just few points in this big volume. It means that the probability is not changing very widely, and you can actually interpolate well. It also means that the architecture that you use is well tailored with the kind of variation that P0 of x has. So it means that, so I would say it's usually machine learning, it means that the architecture is somehow actually related to the structure that you have in the data or to the structure of this high-dimensional probability distribution. But this is something on which people have ideas, but it's not, it's not problem solved. I would say that here there is another problem, on top of this, which is if everything works like should work in the theory, what we should get at the end is the peak, is the image on which you have trained the system. So actually, the model that works, they works because they are not following exactly what the theory says. So that's another mystery.
And they have to do it in a very clever way that magically reproduces.
Exactly. So they have to do it because, of course, you cannot. You can produce something which is not the sum of delta peaks, but then it's complete garbage, so it's not good. So they should do it in a way which is a good interpolation. But this will be the topic of my third lecture, on which I think everybody is working right now, so I can just give you some idea. It's not that it's a problem which is solved.
Other questions? Yeah.
So you fix the temperature to 1. Is lambda playing a role of temperature, or there's something like, do you have a parameter which kind of tunes the noise on your?
Yeah, so lambda, well, it's not exactly like the temperature, but you're right that, so this is going to come back in actually something that I want to tell you right now. It's true that you can do, you take this equation, but you can do, since when you go back, you discretize, and you discretize uniformly, you could say, if I accept that I discretize uniformly at the time when I go backward, maybe I can change the clock. I can change the time. Maybe I can take a temperature which depends on time. Maybe this will actually help. And in practice, what they do is that they optimize this thing. So I just didn't, this is just a hack that they use. But yeah, so you can change the temperature as a function of time, and you can change the parameterization of time in such a way that things are, let's say, better given the resource that you have. But so now this opened the question in, how much can we generalize this idea, and how much actually this idea are connected to other problems actually in science, which is, let's say, probability in this case, and physics. So let me first say a few generalization. So. So the first generalization, which is what they do in practice, to come back during the forward process, during the backward process, you can, it goes after. So when you go backward during the backward process, you can use a Langevin equation. But actually, you can also use a flow equation, so just a dynamical system equation. And so there is a way in which you use an ODE to go backward. And this is very much used. And so let me show how it works. So why we can go backward using an ODE? Well, it's quite simple, is that we always write, let's write again the backward probability distribution in this way, d tau, which is equal to dx minus x minus twice dx of log of p, and this is the p of t of tau. You remember, or let's be p of x of t of tau applied over p of tau. My notation is changing in time. Okay, so this is the backward Fokker-Planck equation. And now, well, remember, this term here, what is it? I can rewrite it. This is what we use. I can write like px of t times the derivative with respect to x of px and t. And the px and t is the same thing of p tau backward, because we have time reversal. So this means that actually this term here I can read it like this terms times this is just minus 2 the derivative of p backward tau with respect to x. Okay, so it's just minus 2 this term. So actually, I can rewrite this like dx of, let me get the sign right, is minus x of minus the derivative of log of p of x and t and tau dx applied to p of backward of tau. Okay, you can just rewrite this equation in this way. Say it again. So this term I transform this way, since the solution, I know that px and t is the same thing of p tau backward, because this is the time reversal. This goes away. So this term is just minus 2 this term. So if I take this, just transform this minus 2 in minus 1. So this is what I get. But this means that now I can interpret this equation like p tau b dt d tau is equal to minus dx, a velocity field v of tau of x of p of tau backward, which is a flow equation. So which means that to go backward, I can go backward in two ways. I can go backward using the Langevin equation, which is dx d tau equal to equal to x plus twice the score s of x and t of tau plus noise. Or I can go backward using the equation which is dx d tau equal to the velocity, which is x plus s of x and t of tau. So now, in this case, I pick, to go backward, I pick an initial condition, which in the case of Uhlenbeck is going to be a Gaussian, white noise. And then I run, using this thermal noise, this equation. Here there is no thermal noise, so I just pick an initial condition, a Gaussian. I run the flow, and at the end, this flow will end in a point, and this point is the new image. Okay, so you can do it both ways. And there is really this...
and there is a factor 2?
And there is a factor of 2. So here you have the 2, and here you don't have the 2, but you don't have the noise. Yeah. Okay, so this is the first generalization. Okay, it's not a big generalization, but I think it's useful to know also because they use it a lot. This flow equation is used a lot in practice. Now, there is a nice way actually to understand all this, to put a general framework on this diffusion model, and which is really what it is related to transport of measures. So we are taking the initial measure, we transport, and then we want to go back. So this is the idea which has been introduced by, actually in a paper by Interpolance. So it's Interpolance by Albergo. And actually I realized that I didn't give any, I always get it wrong. 2023, I think. So I didn't give you any reference for the moment. I will send the reference to Thierry so that he can just put, so if you want to read the original paper and also some review. So the idea of the interpolance is the following. So if you look at this equation, here you have x of t. So the way in which you transport the measure is that you take the initial measure, the initial variable, you squeeze it with this exponential, and then you sum to a Gaussian with this factor. So you could say, okay, maybe I can do something different now. I can take x at time t, which is going to be equal to, let's say in the simplest case, sorry. Yeah, in the simplest case will be something like 1 minus t times x0 plus t, and then a variable, let's call it x1, and t now it's in 0, 1. Okay, so at time t equals 0, the probability distribution, so x of 0, this is distributed like p0 of x. And time t equal 1, so this will be x of 1 will be distributed like p1 of x. Now you see, it's just, you can actually change the time, reparameterize time, to, if I use x1 as a Gaussian, I can actually, what I wrote there can be written, can transform, I think, Actually, you can do it even more generally. So let's say x of t you can write it like an alpha t x0 plus a beta t x1, and then you play with alpha t and beta t in such a way that you transform the measure from the initial one to the final one. And you see that now x1 doesn't need to be a Gaussian, it can be what you want. And this, within this framework, you still have this, it enjoys all the property that I told you, so you can define the equivalent of the score function, you can learn it, and then you can come back with an ODE or with an SD. Okay, if you want to, in general, if you want the ODE, you see here x1 does not depend on time. So x1, someone asked me before, g of t are correlated in time. So this I should put something, a variable which is correlated in time if I want really to go to have diffusion model. But you can also put something which is not correlated in time, it's just fixed. It's just fixed x1. Still, you can go back with a backward process with an ODE. Okay, so this is, I think it's a nice, more general formulation. It tells you, okay, this is just a particular case of transporting measure in a linear way from one measure to the other. Okay, so now I think actually I have time.
And does this have better performances than the diffusion model, or what's the point?
No, I think it's.
What is the question?
The question is whether this has better performance. No, it just. I think it's just a way to, to give a more general mathematical structure, because in practice, people that started from this, they knew that, here I put white noise, I can put something else in such a way that I transform this probability to another one. I can put something more difficult here. So they just knew it, but they didn't formalize with a general way like this.
No, on the contrary, this is less general than that.
Yeah,
this is put something more complicated than Einstein-Nuremberg will never have.
You're right. Okay, but now this is actually useful to make the connection with RG. And if you don't have other questions, so now for the moment I would say, this is also, when you write it this way, actually you can see, if you know what stochastic localization is, you might see the relation between the stochastic localization, but I'm not going to tell anything, so if you know it, you see it, if you don't, well. Okay, but so this is just to give you different extension of these diffusion models. Now I would like to make the connection with RG, because actually diffusion models is really, really related to the RG procedure.
So what is
RG, sorry, randomization group. I will, I'm sorry. You are not exactly a 100% physicist. Now, this relation with RG will also show how much this field is interdisciplinary, because I think it has been discovered in many different ways. So it has been, I will give you a reference, as I say, but I say it first started from people in high energy, actually a PhD student, I think in 2018 or 16, that started to think about it, and he had the first intuition that there was maybe a connection. And then actually very recently, I think 2023, there was been established a real connection between diffusion model and randomization group. This, let's say, from the physics branch. But then actually from probability theory, actually Thierry and co-workers actually had seen from completely different reasons the connection. And then Thierry told me that actually there is an history and there are, let's say, pre-connection even before that. Okay, so what is the idea? So diffusion models and randomization group. So, okay, let me write things in this way. So I will use the notation, instead of using x, let me use x, so x and xi. Let me use the notation that we do in physics. You have a field. So you have a phi, so it's a phi of r. Okay? It's the same thing. I mean, when you have an image, it means that you have the position r, and phi is the value of, let's say, would be the value of the pixel at position r. But I mean, in field theory, when you do field theory, you have a field, and you want to do randomization for this field. The same thing. So phi, the component that you have here are the components that you have this. Is it clear or not? Yeah, okay. Okay, now imagine that I construct an interpolant in this way. So I go in Fourier space. So instead of having phi of r, I go in Fourier space. So I have a phi of k. K is the wave vector. And then I have phi of k at time t. It's going to be, and t will play the role of the renormalization scale. It's going to be equal to k of p and t times phi of 0, okay, plus square root of k of p of t, 1 minus k of p of t, times a Gaussian, which would be just g of p. So for each gp, okay. Sorry, so let me see the okay. So for each Fourier component of the field, I do the linear interpolation between the original component times a constant, I mean, which in principle depends on p and t, but it's not stochastic. And then I have this term here times g. Okay. Now what is this kp of t? So k p of t, it's a function. I'm sorry. No, okay, I see now my problem with notation with p and k. Okay, that I think I wanted to use p because I have a big k here. P, okay, p, and now this is p. Okay. P is the Fourier component. Yeah, it's just because everybody uses this big K, but the K in general is okay.
But Kp, the P is the same P as.
No. So K, okay, K. Oh. Okay, I try to use another function, then I will get completely wrong. So let me call it H. Okay, I hope it helps. I mean, it doesn't help me, but I hope it helps you.
The subscript P that you put to H.
H of
the subscript of the
question is about the subscript, not about the key.
Okay. Let me. Okay, I know that. Okay, let me think. So, H, P of t. No, it's fine. H is a function of P and t. That's fine. Yeah. No, it's the norm of the vector. So it's good. This wasn't wrong. Okay. Okay, so what is this HP of t is this kind of function. So here I have a lambda of t. So this is 1, this is 0, and this is a function of p, which is, is the absolute value of p. Okay? Okay, so and lambda of t, what is lambda of t? So lambda of t is something that is going to be equal to infinity when t goes to infinity, and to 0 when t is going to 0. And it's just moving, actually, just moving. So it's at time t equals 0. Let me see if I get it again, if I'm getting it right or getting it wrong. So now when time t is 0, sorry. Should be 1. Yeah, it's okay, it's all right. Okay, so lambda of t is moving this way when I increase time. Okay, let's see what it does. So in words, which are better than my notation. So at the beginning of time, HP of t is equal to 1 everywhere. So if HP of t is equal to 1 everywhere, what happens? This is 0. So when t is equal to 1, is close to 0, phi t of p is equal to phi 0 of p, okay? For any p. And then when actually t is very large, let's say infinity, phi t of p, what it is, actually is almost 0. It's almost 0 because, well, h is becoming, it's 0 here. I mean, it's the h, this one come here, h is 0, and it's actually, let's say it's a tiny Gaussian. Okay, now let's say also in words, what's going to happen to this measure, it means when I am at time t, now at time t, and I ask what is the probability distribution of phi p of t. So this probability distribution is such that all fluctuations on scale, let's say, on Fourier scales less than lambda t are like in the original theory. And then all fluctuations on Fourier scales which are larger than lambda t are 0, or almost 0. Okay, this is just because when I fix lambda t, well, all the scales, all the p which are less than lambda t, they get 1, so it's the same reason the reasoning than before. All p which are larger than lambda t, they get 0. So what this is doing on
H is a cutoff function.
H is like a cutoff function, exactly, energy. So what is this interpolation is doing is really doing what you want to do when you do RG. When you do RG, you say, okay, I want a theory. I mean, when I've done RG until a certain scale. Now the theory should be correct, should give you exactly the same observable on large scale. And then in principle, all the other ones on smaller scale, you just don't care because they have been integrated out. Yeah?
Is there some assumption of translational invariance using Fourier transforms?
I mean, yes. I mean, we are. So yes, in the sense that in this case, I'm just thinking to model in which you have a translation invariance. So I work in Fourier space. But it's.
I look at images where always in the center there is.
I'm sorry. So in images, in practice. Okay, so let me go back. So here I was thinking more to physics. So this is why. In images, in many cases, actually, you take images and then you translate them in all possible directions just to augment. It's called augmentation. So it gives you more images. So even if you start with a data set with images centered like this, then you translate them, so you increase them. So at the end is translation invariant in many cases. Okay, so what this thing does, it does exactly what RG does. And so it's a way, and now this, when I write it this way, actually, there is a way to rewrite, so it's like an interpolant, but if I want, I can write a stochastic equation, so I should just put something which now depends on time here.
So, Giulio,
yeah.
Where is the flow here? Because phi naught is unaffected. While in principle, if I integrate my high Fourier modes, I would want to modify my parameters so that I get the...
Okay, so let me come back. I come back in just in a minute. So just what I wanted to say is that here I wrote it as an interpolant, but actually I can show that I can write an equation which is d phi of p dt, which is equal now to a certain function. Let me call it ap of t times phi of p and t plus another function b of p and t of eta of p and t. So there is an Uhlenbeck process. If I choose, I mean, I should choose carefully A and B. They are related to this H that I have there, in such a way that this I can implement this. Just I take the initial configuration, I run the stochastic process. So RG now is done like a stochastic differential equation in time. Instead of saying that I coarse grain, I integrate out. So what is just the stochastic process, it just does this. Now, coming back to your questions, and since I will stop on this. So where is the RG in this? So you start to see the RG in the sense that when you move time, you are changing the probability law. And the probability that you reach at time t is the one that you would like to have, is the one that gives you all the correct observable on large scale and all the, large spatial scale and nothing on small scale. Now what you can do is that you define, so now you have a probability at time t of your field phi, and this defines an action which is S of t and phi divided by z, okay? This is your effective action which flows. Now if you write the equation, so if you know what the equation is, let's say you have dt of pt of phi, which satisfies the Fokker-Planck equation. So from this, you can write what is the equation on dt of s of t, which is, let's say, it's a function of s of t. Okay, so you have an equation on s of t. Now this equation, the nice thing is what is called the Polchinski equation, which is the equation that Polchinski derived long ago for exact RG. So here you really have a connection. So I mean, Polchinski came from a very, very different route. So he was using a cutoff function. He was writing how, if I could do RG in exact way, how this action would change as a function of the renormalization scale. And here you see that, well, just with this choice of interpolation, this is exactly the exact Polchinski way to do RG. So this, I mean, I would say it closed the loop. So it shows you that, yeah, you can really think RG like in time, not in the coarse grain. You just add the stochasticity, and you have a dual formulation. And I have to say that, I don't know if you ever tried to derive the Polchinski equation. Polchinski equation is really a big mess. But here, I mean, you use stochastic calculus that, I mean, you know, you learn as an undergraduate. So maybe just to finish, so that I finish and then you ask the question. So you could ask, okay, what is useful for? Okay, it's nice, but can it be useful? So this goes back a little bit to the question of Gerard. So it's the first way to say, okay, instead of taking the usual Langevin Einstein-Uhlenbeck process where these A and B are the identity, this is the first step to change them. And the idea is that actually, if you change in this way, it's good for images because images are multi-scale, like many problems in physics. And if you do this, actually, when the generation process, you first generate a large scale, and then the smaller scale, and then the smaller scale, and then the smaller scale. And this generation, scale by scale, actually stabilizes numerically. I mean, there are many ideas that stabilize numerically the learning and the generation. So it's a good idea. Vice versa, and this is something on which we are working on, is now, if these models are super good in learning the score, what is the score? Well, the score is the grad of log of p, so it's the grad of the effective action. So in principle, you can use this machine learning technique if you have data of your favorite statistical physics model to do almost exact RG. But this, okay, we don't have results, so stay tuned. And with this, I stop, and then I take questions. Thank you.
Any questions?
For me, it's not clear so far why it is RG and not coarse graining, for instance, just on this middle board.
Well, what do you mean? It's coarse graining. It's coarse graining.
But in RG, usually, I mean, you have to yeah, exactly. You have to rescale.
Yeah, exactly. Yeah. So yes, you're right. But so it just means that I mean, the rescaling part is always, so you should learn how to rescale in such a way that the field have fluctuation which are of order 1. This is what fixes the anomalous dimension. But this is part of the RG procedure. So if I have this ST, so if I know how this is running, then from this knowledge, I will find a good way to rescale the things. So the difficult part is not the rescaling, is this one.
Okay. And sorry. And RG about, let's say, a free field, it's a bit weird somehow. But,
no, but it's not a free field. Because you start, so the initial distribution is, let's say, I know, it's a turbulent flow. Then you run this, so you're just, what you're doing is that you are adding noise, and this adding noise, you are doing coarse graining. That's the idea.
I have a question. Many problems in geoscience are inversion, where you know the field somewhere, and you want to know the field somewhere else. And basically, you have to inverse the diffusion equation, or something which has second derivative in space.
Yeah.
They are known to be very unstable in the sense that if you make a small error in the field at the surface, you create big fluctuation, like the inverse problem, the fields that you construct, which are unphysical. In some sense, the backward problem has the same aspect. You have a diffusion equation and you inverse it. Yeah. So do you expect the same instability in the sense that if you make a small error the fields that you inverse, you will create something which is very different from your initial condition?
No, actually, no. This has been studied by a few groups, in particularly Arnaud Doucet, I don't remember, it's Arnaud Doucet and Valentin de Bartoli. And in this case, using this equation, no, you don't have these instabilities. I think I understood why at a certain point, but now I have to think about, so maybe we can discuss
at the break.
Okay.
So I have a question on diffusion models because I have a feeling that the invariant measure, so if you run the forward process, in the end you will just get a spatial white noise, which has the same strength on all scales if you do Fourier transform.
Yeah.
So it seems that your cutoff function HP actually doesn't depend on P. So you're not doing normalization, you're not integrating the small scales.
What do you mean? So it depends on P because when P, I mean, you see it here.
Yeah, but the thing is, if you try to analyze diffusion model in this framework, do you really observe that an HP that is different for a different P?
So I mean, in standard diffusion model, you remember the interpolation that I say. So in standard diffusion model, what you have is that this thing here is exponential minus t, independent of p, and this one is square root of 1 minus exponential minus 2t, independent on p. So standard diffusion model don't make a difference between scale. So this is an upgrade. It's something that was done recently. Maybe I can tell you also the name if I give you. It's by. Okay, I lost. Okay, so this, as I said before, it comes the relationship from probability theory by Thierry and collaborator, but from high energy physics is Kotter and Reznikov, and very recently Mazuki and Ashida. And their idea was, let's do a more general diffusion models in which we treat different scale in a different way. Maybe that's really something which is good actually, and so that's the idea.
Yeah. Thanks for a very nice introduction to the diffusion model. And I have just a lot of curiosity. Is there any other way of, so instead of this Ornstein-Uhlenbach, can we choose other way to get burn motion? What I have in mind is, for example, the underdamped enlargement process. Is it possible to?
I mean, yeah, in principle, I think yes, you could do it in this way. I guess when it's underdamped, maybe you take a little bit more time to go to the to equilibrium. So maybe this is why they don't use this. So I mean, but they try to use other things. So just to tell you, I mean, there are people that use also, I don't know, active. I mean, to make the connection with the lecture of Giulio, you can take active noise, and then well, but then you have to say why this is a good idea. I mean, why this improves on. So for the moment, I would say the only improvement in which people seems to say that it's a real improvement is this thing, treating scale differently, changing the equation. You can change it in other ways. So something that we tried to do is instead of taking eta, we take Levy flights. Yeah, the theory is nice. Now, whether it's useful, it's not clear.
Okay. Yeah. I was just thinking it's like the training process. You can have a stochastic gradient descent, which can be modeled by Langevin over damped, and with momentum, you can also model it by underdamped. And by choosing parameters, it is most of the time will be faster. So that's what I'm thinking about. But I don't know.
You should start.
Curious. Okay. Thanks.
Else, I think we will stop and probably have